Okay, so we're going to prove that if the GCD of A and B is equal to 1, and if we have that C divides A plus B, then the GCD of A and C is equal to the GCD of B and C, which is equal to 1. So let's go ahead and start our proof. So we're going to assume the GCD of A and B is equal to 1, and that C divides A plus B. So Burton tells us to let, as a hint, let D be equal to the GCD of A and C. So this implies that D divides A and D divides C. So using the definition of divisibility, this means that A is equal to dk and C is equal to dq, where k and q are integers. All right, so now we're going to go back to, we know that C divides A plus B. So this implies A plus B is equal to CW, where W is some integer. Now I can see that C is the same thing as DQ. So in this equation here, I'm just going to write that this implies A plus B is equal to DQ times W. Or better yet, using the associative property, this implies that A plus B is equal to D times Q times W, where Q times W is just some integer. So this means that D divides A plus B. Now, I have D divides A and D divides A plus B. So this means, D divides A and D divides A plus B. This implies that D divides their difference, right? So this implies that D divides, let's see, A plus B minus A. Of course, this also means that D divides B, because A plus B minus A is just B, right? So what I have here, so now I have that D divides A and D divides B. So this means that D must divide the GCD of A and B. Okay, but we assumed earlier that the GCD of A and B is 1, right? So this means D divides 1. And of course, if D divides 1, that means D must be equal to 1. So we have that we let D, right, be equal to, we let D be equal to the GCD of AC. So this means the GCD of AC is equal to 1. So we're about halfway there, right, with the GCD of AC is equal to 1. Now we got to get the GCD of BC equal to 1. So we're going to use a similar technique. So we're going to let G be equal to the GCD of B and C. Okay, so this implies that G divides B and G divides C. Okay, but if G divides C, what I know from earlier, right? So let me go up here. I can get actually an A from this equation. I know from this equation here that A must be equal to CW minus B, right? So I can actually get A equal to CW minus B, and what I want is G divides B and G divides A, and if I can get G divides B and G divides A, that means G divides the GCD of A and B, and of course that means G divides 1, and then that means G must be equal to 1, or the GCD of BC equal to 1. So now I know this also means that G divides, let's see, B and G divides CW. So this means that G divides their difference, right? So let me go back. CW minus B, right? So this means that G divides CW minus B, or better yet, G divides A, right? So let me go to the next page. This means that G divides A and G divides B implies that G divides GCD of A and B, which means that G divides 1, and then of course this means G must be equal to 1. And of course, remember we set G to be equal to the GCD of BC. Okay, and then we're done, right? Now we know that the GCD of A and C is equal to 1, right? The GCD of A and C is equal to 1. Well, let me go back actually, right? GCD of A and C is equal to 1, and the GCD of B and C is equal to 1, right? So we have what we set out to do, right? That is exactly what we wanted to show. There's our proof.